Okay, hello everyone. How are you today? Hope everyone stay healthy and uh, in a great condition here and there. I will start today's lecture about multivariate probability distribution 2. Okay. Previously, we were studying about chapter 5.3 marginal and conditional probability distributions, and we checked two examples, and we learned marginal probability distributions and two examples, one for a discrete case and the other for a continuous case. So here's the marginal definition of marginal distribution. If you'd like to calculate marginal probability function for y1 or y2, you can integrate over the other one. So if you want to calculate P1, Y1, you do sum all the joint probability distributions with respect to other variables, and you will get the marginal probability distribution for discrete case or continuous case. In continuous case, rather than summing all the probability mass, you rather integrate with respect to other variables, then you will get the marginal probability. And we saw two of examples related to discrete case and a continuous case. Okay, so let's move on to conditional probability distribution. Here is definition 5.5. This is about conditional probability distribution for discrete random variable. If y1 and y2 are jointly discrete random variables with joint probability functions py1 and y2 and marginal probability functions p1 y1 and p2 y2 respectively, then the conditional discrete probability function of y1 given y2 is you can write it this way. So actually, this is a kind of extension of the conditional probability. In the previously in the previous chapter, we described conditional distribution, which is probability of two sets, set A and set B. This is probability of A intersection B divided by probability of B. Now we want to extend it to the probability function. So actually these are very similar. A given B, and this is intersection, and this is the probability of this is A, B, B, and actually they are the same. Why? Because when we are saying that probability of y1 equal y small y1, what this means is it's probability of the set A, and this set A, this set is y1 equals small y1. So what this set A means, the random variable y1 is small y1. So even if we describe it like this, what this probability of this thing means is that there's sample point corresponding to this set. So in probability there's sample space and there's sets. So there's sets related to this random variable, and so actually these are can be converted as this set inside of that notations. So so that's why this is true, and we can define it like this. Okay. Okay, let's move on to example 5.7 to understand more about the conditional probability distribution for discrete random variable. Refer to example 5.5 and find the conditional distribution of y1 given that y2 equals 1. What it means is that we want to calculate a conditional distribution of y1 given y2 equals 1. We want to find this, and what that means is that is given that one of the two people on the committee is a Democrat. Uh, find the conditional distribution for the number of Republicans selected for the committee. Okay, so um, uh, we want to calculate conditional distribution of y1 given that y2 equals 1. So thus, given that y2 equals 1, uh, given this situation, we want to calculate the probability of y1 equals 0 or 1 or 2. So intuitively, we can divide 8 over 15 to the each of probability so that we can make it as a probability sum to 1. So and actually that's the definition of the conditional probability. So probability of y1 equals 0 given y2 equals 1. Then this is p of 0, 1 divided by p2 1. And here p0, 1 is 2 over 15 and p21 is 8 over 15, which is so 2 over 15 and divided by 8 over 15, which is 1 over 4. And what about y1 equals 1 given y2 equals 1? And this is p1 divided by p2 which is 6 over 15 divided by 8 over 15, which is 3 over 4. And actually that's all because y1 equals 2 is 0. 0 divided by some number is again 0. So p y1 equals 2 given y2 equals 1. This is 0. So we calculate conditional distribution of y1 given that y2 equals 1. Okay. Okay, let's move on to conditional probability distribution for continuous random variable. And here's definition 5.6. If y1 and y2 are jointly continuous random variables with joint density function fy1, y2, then the conditional distribution function of y1 given y2 equals small y2 is this one. And actually, if you remind definition of fy1 distribution function for y1, it is probability of y1 is less than or equal to small y1. So distribution function defined in this way, and so this is extended definition that considering for conditional probability. Okay, and you can also know that f of y1, which is probability of y1 is less than or equal to small y1, and this can be calculated integrating the conditional probability. So probability of y1 is less than or equal to small y1 given y2 equals small y2, and the probability for this is f2 y2 dy2, and y2 is minus infinity to infinity. And here let's say f1 y1 and f2 y2 are density function for each of y1 and y2. Let's say f1 y1 and f2 y2 are density function for y1 and y2, then you can calculate the fy1 this way. And also to calculate fy1, you can do this way as well. F of y1, and this is from minus infinity to y1. You can integrate f1. Since you already have y1 here, I will write t1 rather than y1, dt1. So this is f1 T1. This is density function for y1, and so to calculate f of y1, which is probability of y1 is less than or equal to y1, you can integrate the density function to y1. So which is this one. You can integrate from minus infinity to y1 f1 t1 dt1, and also, to calculate f1 t1 from the joint distribution, by the definition of marginal probability, you can calculate it. You can calculate it from the joint distribution. So we have f1, y1, y2, which actually this is ft1, y2. T1, Y2, and dy2. So you integrate with respect to y2 from minus infinity to infinity. You can get the f1 t1. This is f1 t1 and dt1. Okay, and you can change this integration. Let's have a look. So you have two axes. One axis is t1, and the other axis is y2. And for t1, integration is minus infinity to y1. So here's y1. So and dy2 integration is from minus infinity to infinity. So the area is this one. So from here, for given dy2, integration is from minus infinity to plus infinity, and with this line, we are integrating it with dt as from minus infinity to y1. So this way, and you can actually change the order. So first, if you change this integration with dt1, dy2. So for dt1, the integration is from 0 to minus infinity to y1. So this time dt1 minus infinity to y1, and for this piece we integrate it from negative infinity to plus infinity for y2. So negative infinity to plus infinity, and we have f t1 and y2. Okay, and what we know is that in here, this part and this part should be the same. So we can say that, and this is fy1 y1 given y2 times f2 y2 is equal to integrating minus infinity to y1 f t1 y2 dt1. Okay, and from here you can calculate from here. Oh, I don't have more space. You can calculate fy1 given fy1 given y2 can be calculated as this way. So you can move this inside of here. This is function of y2. So this y2 do not depend on t1. So this can go inside. So minus infinity to y1 and f t1 comma y2 divide by f2 y2 dt1. Okay, so you can calculate this formula, and actually this is what what I show you next. So here's definition 5.7. Definition 5.7 is that for the conditional probability distribution, you can calculate it with a density divided by the joint density divided by one densities. Okay, so let y1 and y2 be jointly continuous random variables with joint density fy1, y2, and marginal densities f1, y1, and f2, y2 respectively for any y2 such that f2, y2 is greater than 0. The conditional density of y1 given y2 equals small y2 is given by this. And actually the derivation, so you can change the order of y1 and y2, which is this thing. And actually from the previous formula, we derived this thing, f y1 given y2 is equal to minus infinity to y1 divide f t1, y2, f2, y2, dt1. And if you differentiate this thing, you can derive uh, this one. If you differentiate each part with respect to y1, t1, y1. So differentiate each part with respect to y1. You will get this formula. Okay. Okay, let's move on to example 5.8. A soft drink machine has a random amount Y2 in supply at the beginning of a given day and dispenses a random amount Y1 during the day. So with measurement in gallons. We initially have Y2 amount and we spend Y1 amount during the day. So it is not resupplied during the day, and hence y1 is less than or equal to y2. This is natural because we initially have y2 amount and we spend y1 amount, so this should be hold. And it has been observed that y1 and y2 have a joint density given by here, and that is the point y1, y2 are uniformly distributed over the triangle with the given boundaries. So here it have constant, so density is constant over the intervals, which means the points are uniformly distributed over the triangle, and the triangle is here y1 and y2, and here y1 is less than or equal to y2, so it's this part, and each of y1 and y2 are from 0 to 2. Okay, so among this triangle, the density is uniformly distributed. Okay, and find the conditional density y1 given y2 equals to, small y2. So we want to find density probability of y1 conditional density, which is f of y small y1 given y2. Okay, so this is the conditional density. So the first problem is find the density f y1 given y2, and the second problem is evaluate the probability that uh, less than 1 over 2 gallon y1 is less than 1 over 2 gallon, given that the machine contains machine initially contains 1.5 gallon. Okay, so the problem is two things. First, find the conditional density, this one, and actually this is f of y1 comma y2 divide by f2 y2. So from this distribution, you can calculate the marginal distribution of f2 y2, and then you can calculate this thing. And about the second part, so this is first one, this is second one. For the second part, we can integrate the conditional density from 0 to 1 over 2, the conditional density y1, given that y2 is 1.5. So d y1. Yeah. So you calculate this, then you will get the answer for this. Okay. I will do it from next slide. Okay, so let's try to solve. The first one is try to find the conditional density, which is f of y1 given y2. And the second one is find the probability of y1 is less than or equal to 1 over 2 given y2 equals 1.5. Okay. For the conditional density, f of y1 given y2, we can calculate it. We have marginal distribution of fy1, fy2. If we divide it with respect to f2, y2, we will get the conditional density. So we need to calculate this one. And for f2, y2, from the knowledge of marginal density, we can integrate it with respect to dy1. And actually the y1 is from 0 to y2. So from 0 to y2, dy1 1 over 2. Okay, and okay, this is 1 over 2 y1 given 0 y2. This is 1 over 2 y2. Okay, so for the interval that y1 is and for here y2 is from 0 to 2. Okay, and so you divide this one from here, which is 1 over 2 divided by 1 over 2 y2. This part cancels, and the area is 0 to y1 to y2 to And actually here, since y2 is given, you don't need this part. When we are having this one, we think that y2 is given, so the density of this thing is actually density for y1. So this is 1 over y2, 1 over y2 on interval. Y1 is okay. So this is the conditional density. Oh, and zero otherwise. Zero otherwise. So this is conditional density, and for the probability of this thing, so um, so for y1, it is 0 to 1 over 2, and we set y2 equals 1.5, which is um, 1.5 is 3 over 2, and so 2 over 3, and dy1, which is 2 over 3, y1, 0, 1 over 2, which is 1 over 3. Okay, so 1 over 3 is the probability. Okay. And homework for chapter 5.3 are these. Next one is chapter 5.4, independent random variables. Let's look at definition 5.8. Let y1 have distribution function f1 y1 and y2 have distribution function f2 y2, and y1 and y2 have joint distribution function f y1 y2. Then y1 and y2 are said to be independent if and only if this holds. F y1 y2 is y1 f1 times f2 y2. For every pair of real numbers y1 y2, if y1 and y2 are not independent, they are said to be dependent. Okay, so this is actually like we can write it like this. Probability of y1 is less than equal to small y1, comma y2 is smaller than small y2, and actually this is same as y1 is less than equal to small y1 times probability of y2 is smaller than small y2. And this part, this is natural because the set related to this event and the set related to that event. So there's corresponding set A and B for these events. And if these events are independent, we can, by definition of independence, uh, uh, we can write it as probability of y is less than or equal to y1, small y1, and times probability of y2 is less than or equal to small y2. So by definition of independence, we can write it this way. And actually, this is f y1 times f y2. So this thing is kind of natural from the definition of independence. And here comes the theorem 5.4. If random variable y1 and y2 are discrete random variables with joint probability function py1, y2, and marginal probability functions p1, y1, and p2, y2 respectively, then y1 and y2 are independent if and only if this thing holds for all pair of real numbers y1, y2. And actually, if you um, these actually you can write it as probability of y1 equals small y1, and if you write this as probability of y2 equals small y2, and this part it is probability of y1 equals small y1 comma y2 equals small y2, then probably you will understand it more intuitively. So there's a set corresponding to this. There's in the sample space there's set for y1 equals small y1, and there's also set for large y2 equals small y2. And if those if it is independent, then this should be true. So this equation would be natural to you, I think. And for the continuous random variable case, if y1 and y2 are continuous random variables with joint density function fy1, y2, and marginal density functions f1, y1, and f2, y2 respectively, then also y1 and y2 are independent if and only this thing holds for all pairs of real numbers y1, y2. Okay. Let's move on to example 5.9. For the diagnostic problem of section 5.2, show that y1 and y2 are independent. And in the previous example of section 5.2, the diagnostic problem is that we have two dice. And let's say the number that's shown from the first dice is y1, and the number that's shown from the second dice is number 2. And so their joint distribution can be defined this way, and we can see that this is Py1, y2, and we can see that P1, y1, which is the probability for y1 equals small y1, it should be 1 over 6, for y1 is equal to 1 to 6, and for P2, y2, its probability of y2 is small y2, which is 1 over 6 again, and and so what we want to do is we want to show that y1 and y2 are independent. And in the previous theorem, if p1 y1 times p2 y2 is p y1 comma y2, then the random variable y1 and y2 are independent. And actually this is true. Let's say y1 is 1 and y2 is 1, then 1 over 6 times 1 over 6, p1 1 times p1 2 1 is p 1 1. And actually it is true for any combinations of y1 and y2. So by theorem, the previous theorem, we can see that y1 and y2 are independent. Okay, let's move on to example 5.10. Refer to example 5.5 is the number of Republicans in the sample independent of the number of Democrats. Is y1 independent of y2? So the joint probability distribution py1 and y2, is described in this table. Okay, and the py1 and py2 are these. So py1 is this part, by the marginal probability py1. So the table describes the joint distribution, and the each column total or row total, they are about distribution for y1 and y2. Okay, so let's check one by one. So is the if y1 is 0 and y2 is 0, y1 is 0 and y2 is 0, then p1 y1 times, what is p1 y1 times p2 y2? It is um, it is 3 over 15 times 6 over 15. And what is the joint distribution? That is P00. Actually, this is okay. P00. This is 0. So they are not equal. And so they are not independent. So here, y1 and y2 are not independent. Okay. Okay, let's move on to example 5.11. This time the distribution y1 and y2, they are continuous random variables, and so okay, here the joint density, and we want to show that y1 and y2 are independent. And to show this, we need to find the marginal distribution for y1 and y2. So we want to find the marginal distribution f1 of y1, and this is we can get this marginal distribution by integrating it over the other variable, which is y2, and y2 is from 0 to 1, and 6y1 y2 squared dy2. And this is so for this integration, 6y1 can be go outside. 6y1 is not dependent on y2, so we can move this out and integrate this part, which is 1 over 3 y2 third, and from 0 to 1, and this is 6y1, and we put 1 to y2, which is 1 over 3, and minus 0. And so this is 2y1. So this is 2y1, and y1 is from 0 to 1. Okay, what about f2, y2? F2, y2. We integrated with respect to y1 this time. dy1, and this time y2 square is not dependent on y1, so we can and this is constant. 6y2 square is constant. 6y2 square is constant, and integrate y1, which is 1 over 2 y1 square 1 0, and this is 3y2 square 3y2 square, and since we put it here from 1 minus 0, 1 over 2, and 1 over 2 times 6, it is 3. So, and 3y2 square, and y2 is from 0 to 1. Okay, so we derived the marginal distribution density function for y1 and y2, and what we can see is that f y1 comma y2, is it true? f1 y1 times f2 y2, is it true? And actually, yes, this is true. 2y1 times 3 y2 squared, which is 6y1 y2 squared, and the domain is also the same. And so we can say that y1 and y2 are independent. And for independence, we can also write this way. Okay. And let's move on to example 5.12. Let fy1, y2 are like these, and show that y1 and y2 are independent. So this time, fy1 and y2 is defined on, so this is y1, this is y2, and they are from 0 to 1, and also y2 is less than or equal to y1. So here, this part, this is y1, and this is y2. y2 is less than or equal to y1. So this part defined on this part. And let's see. So, so let's calculate one by one. What is f1, y1? f1, y1. We integrate it with respect to y2 and with respect to y2, which is 0 to y1. And it is 2 dy2. Okay, and this is actually 2y2, and from 0 to y1, which is 2y1, and the interval is from 0 to y1. Yeah, so okay, this is the density function for f1 y1. And what about f2 y2? f2 y2. Similarly, for we are integrating with respect to y1 this time, and for y1, y1 is from y2 to 1. From here, y1 is from y2 to 1, so y2 to 1 and 2 here. And this is 2y1. We are integrating with respect to y1, so now it is 2y1, and from y2 to 1, and so this is 2 minus 2y2, and for y2 it is from 0 to 1. Okay, now let's see, is it true? Is f1 y1 times f2 y2, is it true? F y1 and y2. Actually, this is not true. So y1 and y2 are not independent. Y1 and y2 are not independent. Okay. Okay, now let's learn about theorem 5.5. Let y1 and y2 have joint density fy1, y2 that is positive if and only if y1 is from A to B and y2 is from C to D for constant A, B, C, and D, and f y1, y2 are zero otherwise. So we can see that there is joint density fy1 and y2. Then y1 and y2 are independent random variables if and only if fy1 y2 is equal to gy1 times hy2. And here, gy1 is non-negative function of y1 alone, and hy2 is also a non-negative function of y2. So this is a more weaker version of the previous theorem. So in the previous theorem, y1 and y2 are independent. y1 and y2 are independent if and only if fy1, y2 is f1, y1, and f2, y2. If this is true, y1 and y2 are independent. But we have the weaker version. If we can find any function g of y1 and h of y2. G and H are no need to be the density function, and uh, and and here one more restriction is that y1 and y2 should be defined in the ABCD range, but if we can for the joint density function, if we can um, express this as gy1 and hy2, then we can say that they are independent. So it is much easier to show than this one. For the to use the previous theorem that we learned, we must show the first part and second part are density functions, but with this theorem we just need to show that we can f the joint density function is product of two functions. One is related to y1 and the other is related to y2. And for the proof for this theorem 5.5 I will skip, but this would not be very difficult because this gy1 with y1 ranging this one, probably you can modify with some constant to make it a density function for y1, and also with this constant you can modify h of y2, you can make it y2 f2y, and so and also some other mathematical notations to exactly show why this one holds. But for now, I will skip the proof and move on. Okay, here is the example 5.13. Let y1 and y2 have joint density given by this. Are y1 and y2 are independent variables? And here, if we can define gy1, if we can define gy1 as y1, and if we can define hy2 as 2, and also y2 is from 0 to 1, and y1 is from 0 to 1, and then what we can say is that y1 comma y2 is actually gy1 times hy2. And so by the previous theorem, we can say that y1 and y2 are independent. Okay. Okay, refer to example 5.4. Is y1 the amount in stock independent of y2, the amount sold? And in the previous example of 5.4, this is the density function, and this time actually the interval defined in the interval for the density, this they are not for the constant form like this, and so we cannot apply the previous theorem, and so to show the independence we should use the we should calculate f1 y1 and f2 y2, and f1 y1 is actually we can calculate f1 y1, we can integrate with respect to y2, and for y2 it is from 0 to y1, 0 to y1, 3 y1, and this is 3 over 2 y1 square. Oh, y1 y2. Integration is with respect to y2, so it is okay, 3y1, y2, and y2 is from 0 to y1. And so this is 3y1, and y2 is y1 minus 0. And so this is 3y1 square. Yeah, okay, 3y1 y2 square. And y1 is from 0 to 1. And what about f2 y2? f2 y2. This is, so here we are integrating with this respect to y1 this time, and y1, the range is from y2 to 1. So y2 to 1 and 3y1, and we are integrating with respect to y1. So 3 over 2 y1 square and 1 y2. And so this is 3 over 2 minus 3 over 2 y2 squared, and y2 is from 0 to y1. And so f1 y1 times f2 y2, so f1 y1 times f2 y2 cannot be expressed as like this, so y1 and y2 are not independent. Okay. Okay, homework for chapter 5.4 are these. And thank you very much. See you in the next lecture.